Ah, okay. All right. All right. Ah, 3 viewers. 8. All right. Welcome back to class. I suppose I should be playing this random music. Let me play this. Okay. So, what do we got here? So we're talking about group theory, right? And I have to give 45-minute lectures, right? I give 45-minute lectures, so I have to just kind of be one-pointed and focused on what I'm saying. So I apologize for not being able to chat about anything not related to the material for the first part, and then afterwards I'll interact with you all some more. Okay, so I want to talk about 3 things today. So I feel like this rule of 3 seems to be good for this 45-minute fast lecture thing. So the first thing is I just want to keep talking about homomorphisms and isomorphisms between groups. Then our sort of main theorem for the week, Lagrange's theorem on the order of a subgroup dividing the order of the large group. That's Lagrange's theorem, and one of the most important concepts behind the proof will come up today, the concept of a coset of a subgroup. Left and right cosets. Okay, and then we'll just go back to concrete, hands-on. Let's go investigate the symmetric groups, or the permutation groups, as some other people call them. Okay, so let's begin. Homomorphisms. Homomorphism. Okay, so I'm going to prove some basic things about homomorphisms real fast. bunch of baby facts. Bunch of baby facts. So remember, the definition just said, the definition of a homomorphism from one group to another, G and G prime, is a homomorphism if it respects the group structure on both sides. All right, so we're going to write that just like this. I'm going to use dot to denote the group law on G and on G prime because I don't want to use different symbols. You have to tease out where a multiplication is happening. All right, so that's it. This thing respects multiplication on both sides. It lines up the multiplication on both sides. Okay, so from this simple property, you get some facts. Let's go through some facts. Fact number 1. A homomorphism must send the identity element to the identity element. So f of E must be E prime, the identity element of in G prime. All right, so that's that must be the case. So how do we know that? Because let's just check it. So f of E times G. I mean, we don't even have to do this, but here, let's do it. Let's do it even more elegantly, minimally. Let's do f of E times E. On the one hand is f of E, because E times E is E. But on the other hand, it's f of E times f of E by group homomorphism. And so whatever this element is in the group, in the target group, it is its own square. And so cancel or multiply by f E inverse on the left on both sides, for example. That's what cancel, left cancel means. And then you get E prime equals F. All right. So if you respect the group law on both sides, that means you better have sent the identity to the identity. That's just a consequence. Okay, another simple fact too. F of G inverse is F of G inverse. The inverse of an element gets sent to the inverse of the output of that original element. Okay, respects inverses. Okay, because of this, so you just write down a sequence of true facts and you stare at it. Well, f of G times G inverse, on the one hand, is f of E, which we know is the identity from previous part. But this is also f of G times f of G inverse by the homomorphism property. And so here it is. This element, this thing, is the inverse of f of G. And that's all we're saying. This element is the inverse of f of G. So that's the proof that inverses get sent to inverses of respective elements. So this homomorphism property implies these other things, is the point. All right. So the last thing I want to say about sort of abstract things about homomorphisms, abstract little baby comments, is two observations. These are important, very important. They're simple but very important observations. All right. So I should probably define two things. So the first thing I'm going to define is the image of a group homomorphism is simply the set of outputs. Just the set of all outputs of every, as you vary across all inputs. All right. Homomorphisms don't have to be surjective, so this could be a proper subset of G prime. So that's the image, just all outputs. Okay, and definition number 2. The kernel of a homomorphism, the kernel of a homomorphism is the collection of inputs that get sent to the identity is equal. So it's denoted ker f is kernel of f, the set of elements in the domain such that the output is the identity element. All the things that map to the identity under the group homomorphism, that's a subset of the domain, and it's called the kernel. All right? So here are some very basic facts, 2 important facts. 2 very important facts. The image of a homomorphism is a subgroup of the target group, G prime, and the kernel of a homomorphism is a subgroup of the domain group. Images and kernels are subgroups of the respective group. So image is a subgroup of G prime. This is a subgroup, not a random subset. And kernel in G is a subgroup. Okay? So these proofs are absolutely boring. Okay, so let's do image, for example. Image. Why image is a subgroup? You're supposed to take 2 elements and argue that their product is still in the image, and an inverse of an element in the image is still in the image, and the identity element is in the image. So identity E prime is in the image. Oh, we call it image of F. That's notation. So we also use image of F as notation. But you can just also use F of G as name for image too. The identity is in the image because of fact number 1 here. All right? F of E is the identity. So identity is an output. Great. Inverses. So if A is in the image, is A inverse in the image? Yes, because A is F of some element, G. That's what it means to be in the image. And so, F of the element G inverse is the inverse of A, thanks to number 2 that we proved earlier. Okay, great. So, inverses stay within the image. Awesome. Okay, is the set of image output elements closed under multiplication? So closed under multiplication, group multiplication, right? So if A and B are both in the image, is A times B also? Yes! Because A is F of G for some G, and B is F of H for some H. And so, if you look at f of g times h, by the fact that f is a homomorphism, notice how you got to use that. Homomorphism says this is f of g times f of h, which is a times b by hypothesis. And so indeed a times b is the image of some element in the group G, right? So image is a subgroup. Done. Image is indeed a subgroup. Awesome. Hello, hello. Okay. So kernel. Next, why is the kernel a subgroup? Why is the kernel a subgroup of the domain group? Okay. Question number 1. Is the identity element in the kernel? Yes. Because f of e is e prime. That was the first thing we proved. All right? Because this identity element does get killed. We think of it, some people say kill the element, meaning send it to the identity. Because sometimes the identity is called 0, in like certain groups, became 0. Linear algebra, you had the notion of a kernel of a linear transformation. Exactly the same situation, because a vector space is, after all, a group. All right, next, 2. Let's see. Inverses. If some element G is in the kernel of F, is G inverse in the kernel of F? Yes. Because if G is in the kernel of F, that means that f of G is the identity element in the target group. Okay. But now if you look at f of G inverse, that's the inverse of f of G. That's the second fact we proved today. Which, by hypothesis, is the inverse of the identity element, which is of course the identity element again. So G inverse, in other words, is also killed by the homomorphism F. It's also sent to the identity. So G is in the kernel implies G inverse is in the kernel. Wonderful. Okay. So 3. If two elements are in the kernel, is their product in the kernel? Wow. Yes. Yes, it is. So here's why. We know that f of G is E prime and f of H is E prime. That's by hypothesis. That implies that f of G times H is, thanks to homomorphism, this is not some random function between two sets. It's a homomorphism. Very delicate. It allows us to do this. F of G times H is that product, which is, by hypothesis, E prime times E prime, which is E prime, of course. And so, indeed, the product remains in the kernel. So when you have a homomorphism summary, you get just naturally two subgroups are born. One subgroup is in the codomain, the target group's world, and the other, the kernel, is in the domain group. You get these two little subgroups, or big, or trivial, or whatever. And so we'll be using image and kernel all the time when we face a homomorphism in the wild. Okay, so once again, I'm going to leave the discussion of homomorphisms now. So I'll leave homomorphism world. But I want you to continue I just want to remind you, continue trying to find isomorphisms and even homomorphisms that aren't isomorphisms. More generally, homomorphisms among all the groups that you know. You have now a huge bag of groups. I showed you the product operation that produces a new group out of two groups. So you've got like at least 5 groups. Go and try to find as many homomorphisms and isomorphisms among them as you can. This should be a lifelong practice every morning. Okay? So there you go. Keep doing that. And now I'm going to go to the second chunk of the lecture, which is the march towards Lagrange's theorem. It's a change in topic, okay? So let's change topics. So if you need to, you should stretch. You should get up and stretch, move around a little bit, changing to topic number 2. All right. So Lagrange's theorem said, or Lagrange tells us, that the order of a subgroup, if H is a subgroup of G, finite group, then the size of the subgroup divides the size of G. All right, brilliant. Okay, so what happens is, so what I want to talk about today arbitrary, that's right. Or you can think of the center as some kind of thing to point at, which when the center is the whole group, you know the group is abelian. But when just because of that, if the center is really small, it's just one way of thinking that the group is kind of very much not abelian. But there are different ways of measuring abelianness, and I don't want to say one is better than others. Okay, so yeah, you can think of it that way. It's a way of thinking. It's not some theorem, arbitrary. It's just, it's so that human beings have a chance at life, at understanding the wonderful cosmos. We start to say like, okay, because if the center is all of the group, that's exactly the abelian situation. Because of that, you can extrapolate and think if the center is small, group is far from being abelian. But there's nothing precise about that statement. Okay, next. Lagrange's theorem. What's underlying Lagrange's theorem is not... Okay, the divisibility fact is great. It's fantastic. Fantastic. However, the underlying principle behind Lagrange's theorem is much more important to understand. So what's the underlying principle? The underlying phenomenon / picture, which implies Lagrange's theorem after you make a certain observation. So this is a more important concept I'm about to tell you. So what's the underlying phenomenon / picture? Okay, so what's our situation? Our situation is we have a subgroup of a group. If you need an example, let's take a running example. So for example, G could be the integers, the infinite cyclic group. The integers, okay? And H could be the subgroup of multiples of 6. Why not? Multiples of 6. All right? Or you go and you do your own. Okay, G could be the dihedral group, D3, for example, and H could be the rotations, for example. You have tons of examples in your list. So that's the situation. All we have is a group and a subgroup. And notice that I chose an infinite example as one of my examples, and that's because this underlying phenomenon and picture is true outside of the finiteness hypothesis. It's just generally true, super general phenomenon picture. Okay, so you have a group H, a subgroup in a group, and so what you do is you try to draw this situation as best you can. Oh, here's a group. And you know, the group has this identity element, and all we know is the subgroup is something like this. Okay, this is actually a terrible drawing, because I'm about to draw something that I can't do with circles. Maybe Smash Time Fools will be able to do this, but I can't really tile this big circle by smaller circles. But Smash Time Fools knows how to do this very well. Okay, so I'm gonna draw just like some vague blob. Okay, so this is a subgroup, H. And so what I'm about to explain to you is when a group sits in a subgroup, then in some sense, the whole group is gonna get tiled as a set by certain carbon copies of H. Carbon copies of H that perfectly tile the ambient group G. So what we're gonna introduce are a bunch of other subsets, carbon copies that perfectly sort of subdivide and tile H. All right, I'm gonna tell you what these question mark subsets are. The question mark subsets are disjoint from each other. They don't overlap. They're all in some sense similar to H. They're all kind of shifts of H. And they all cover, altogether they cover the group G. This is called a partitioning of the set G. A partitioning is born once you have a subgroup of a group. That's the fundamental principle. And these little pieces are called cosets. Each of the question marks, these are called cosets. And now there's going to be the word left and right placed in front of the term coset. Okay? So here's the definition of a left coset. I think this is the left coset. Today, I'm going to call this left coset. It is what it is, all right? So the definition is clear, but whether I call it left or right, I think there's maybe some debate. I'm not sure. Okay, so here's a definition. Okay. Pick any element in the group. Then the left coset attached to G, the left coset of H with respect to G, I don't know. Okay, with respect to G, I don't know how to say it anymore. It's been like 15 years. The left coset of H with respect to G, or however you want to call it, is, this is the definition. You read this thing, okay, it's this. The way you write it is you write G on the left, and then you put the subgroup next to it, capital H. And this is a little multiplication between G and capital H. But what we mean is the totality of elements, which are G multiplied by an element in H. So you take all the elements in H, the left coset of H in G, but attached to this little element, little g, lactose intolerable. I don't know how to say it, but it's this. Put the little g on the left, slap the whole set, the whole group H, and take all those multiplications and circle them. Okay? That set is a left coset of H. This is called a left coset. All right? For this lecture. I'm going to call it a left coset. It's G on the left times H. Okay? So, example. Let's do an example. It's great. Example is good. So we've got our group G, and we've got our subgroup of only the multiples of 6. Okay? So let's draw this. Let's draw the number line from kindergarten. If you looked on the top of the classroom wall, all along the edges, you'll see this. You'll see that they put the infinite cyclic group on the ceiling like this. They were preparing you for this class, so they went ahead and drew the infinite cyclic group. Absolutely lactose intolerable. Absolutely. We're shifting the group H by hitting it with G on the left. We're sort of shifting it. But look, you'll see the shift right here. You'll see it in this example. And now look, the subgroup H in orange is six was too big. Six was too big. Okay. 6 was too big. Let's do 3. Let's do 3, folks. Let's just do 3. Let's do 3. Okay. Let's draw the number line. Okay. -1, -2, -3, -4, -5, -6. Okay. Okay. 3z. Multiples of 3. 0, 3, 6, 9, 3, 6, 9. So orange. Orange is the subgroup. Now pick your favorite element. Let's pick G equals 1. Pick your favorite element. Here, pick this. So let's take G equals 1 in this group. All right? Now, what is the left coset of H corresponding to the element 1? Okay. Left coset, our multiplication law is adding, right? So what is 1 plus H? This left coset. 1 plus H. What the hell is it? All right. It's every element of H plus a 1. That's what it is. It's 1 plus everything in H. So you get 1 plus 0, 1 plus 3, 1 plus 7, etc. This. So this blue set is a left coset of the orange set. Is a left coset of orange set. Orange subgroup in our example. Notice that you took the subgroup and you kind of shifted it by one element called G. All right, fantastic. Okay, yes, same joke, awesome. All right, next. So what do left cosets look like? How do the left cosets sit in the ambient group G? That's the basic question I'm gonna answer. So how do left cosets? By the way, the definition of a right coset is the set of all elements where you multiply G, one fixed element on the right, and you let all elements of H multiply it. So that's the right coset definition. Okay. So how do left cosets look in the group G? So that's a vague question, but we're gonna introduce some very basic properties that all of you need to learn and have. You need to know how to prove these things. Just it should be flowing through your veins. So here are some properties. Here are some neat facts. Neat fact. All right, here's a neat fact. If you have one element contained in that left coset, if you have an element that happens to be in that particular translate of H, the Y translate, the left Y translate, then Y is also contained in the X translate of H. Okay, so there's your first little fact. If you have X being in a Y translate, then Y is also in X translate. So obviously this is an if and only if. It's an if and only if condition because you can swap the order. All right, so proof. X in YH means there is some element such that X is the Y times that element. All right? But now, carefully, in this whole exercise, carefully trace how important it was that H wasn't a random subset. H had to be a subgroup. Trace that. Okay. Not plus, times. Because we're not in a commutative group necessarily. Great. So X is Y times H for some H. Therefore, X times H inverse. Notice, I hit this equality on the right by H inverse. Multiply on the right by H inverse. And then you'll get my next sentence. This is Y. But look, Y is the element X times an element of H. This is in H again. Wow! Wow. So, Y is indeed in here. Done. All right? So, that's the first thing I wanted to show you. All right? If X is in the if you have an element in Y's coset, then Y is in the corresponding other one's coset. That's some sort of thing. All right? So here's another fact. Another simple fact. Another fact. Another baby fact. When are two cosets the same? When is this coset equal to this one? All right? When is that true? What is the ambiguity in labeling a coset by A or by B, etc.? What is this ambiguity? All right, so if this coset is equal to that coset, then obviously A times 1, which is an element clearly in here, A times 1 would be in BH. Would be an element of B times H. Great. In other words, A is a multiple of B by H. So A is B times H for some H in the subgroup. So that would have to happen. But the argument is symmetric. Also, B would be A times H prime for some H prime. Namely, the inverse of H, actually. Okay? So that's how you can tell when you're looking at the same coset. The same coset might be written in two different ways with two different translators or shifters. Shifter by A, shifting by B. But that might yield the same subset. And the way you know that it yields the same subset is if A and B are in the same coset as each other. That's kind of a tongue twister, but that's how you know you're witnessing the same coset. So for example, like 1 plus 3z is the same coset as 4 plus 3z. And the underlying reason is because 1 and 4 are in the same coset. Left coset. Okay. Now let's look at another baby observation. Very baby observation. Baby observation. Every element in a group G is in some coset. Left coset. Yeah. No, obviously. G is in this left coset. Obviously. Okay? Done. Easy. All right. So actually we have all the pieces now to prove the most basic fact about the cosets. So the most important fact. The left cosets of H partition the group G. In other words, this is the same as saying two left cosets. So two left cosets are either completely disjoint they don't intersect, or they are literally the same set. They snap together and are equal, or are equal. There is no intermediate way that two cosets can intersect without them becoming the same set. Okay, they snap together. So that's the first thing. And two, the whole group is the union of cosets. Is the union. All right, so the fact that the whole group is a union of left cosets is this baby observation. And that number one, this fundamental disjoint or equal, either you're with us or you're against us. That's this property. This property follows by combining the first couple baby facts. Combine this one and when are two cosets the same? It's exactly when A and B are A is B times some element in H, or B is A times some element in H. So you combine this baby fact with this baby fact, and I want you to prove number one using those two facts. Okay? It's a simple exercise to do that. And pay attention to the importance of capital H being a subgroup and not some random kind of subset. Very important. Okay? So, summary. Yes, there's an equivalence relation here. Yes, we'll talk about it in terms of equivalence relations next time. Okay, but this is the fundamental situation that happens when you have a subgroup in a group and you choose left or right. You choose left, then all the left sort of translates of the subgroup H. They partition the group, but a given left translate might have many names. For example, this left translate is like the element 1 on the left of plus the group, subgroup H. But it's the same as the element 4 shifting the subgroup. Sounds familiar from modular arithmetic? Exactly. We're sort of taking modular arithmetic and we're kind of abstracting out the basic abstract situation in modular arithmetic. The modular arithmetic example is only one example of what happens when you have a subgroup in a group. Okay. So we'll talk more about what even in the setting of a subgroup in a group, there are some situations where the subgroup is so special. It's called a normal subgroup, where better things happen. But that's for next week. Okay? So this is the underlying principle. After this, we'll just observe one last thing, and Lagrange's theorem will just pop out. Okay, so the last thing I want to do quickly in the last 5 minutes, I'll go over time. You can watch watch me talk about this during afterwards in the video. You have to go. Okay, so topic 3 I had to tell you is let's play around in some symmetric groups. In the set of permutations on n elements. So this is a permutation group on n elements, on n symbols. Okay, and we're just traditionally, we're just going to use the numbers 1 to n to represent our elements. Okay, it's a set of all permutations. Okay, so let's play around. I'm going to show you one way of labeling each element. So how to label a permutation? How to like point to it? Okay, here's what it is. A permutation is, after all, a bijection from this set to itself. A bijection. A one-to-one, and therefore onto, because these are finite sets of the same size, one-to-one and onto function. Okay, great. So how do you label a function? You label it by like input-output table. So you can label it like this, like in, out. Right? You can do this, like, and you'll just put the numbers 1, 2, 3, 4, like 3. Okay, we'll do S3. And then you have to put the output. Where did 1 go? Where did 2 go in this musical chairs? Where did 3 go in musical chairs? Okay, so 1 has to go, maybe 1 went to 3, maybe 2 went to 1, and maybe 3 went to 2. Notice that this is a bijection. I used every element here. I used every single element. And so that's how you know it's a bijection. Okay, so this is one very clumsy way to label every bijection. You put the inputs and then stick the outputs as a column of numbers. Okay, the book, you can also do it like the book. The book goes ahead and puts this on its side. So the book says you can encode this instead as inputs on the top row and outputs on the bottom. Okay, so for example, this one will be encoded as 1, 2, and 3. The top row is just 1, 2, and 3 all the time. 1, 2, 3, 4, 5, 6, 7, 8. Put them in a row, and then tell me, where did 1 go? Where did 2 go under this function, this permutation function, this bijection that you're talking about? Where did 3 go? And so on. So this 3, 1, 2. Same permutation. Encodes the same permutation. So now let's put another permutation on the board. Okay, very boring musical chairs, absolutely. This is P. Let's say this is P. Okay, the P is an element in S3. This element. Let's put another element of S3 on the board. Look at this, Q. I don't know, I'll just call it Q. All right, it's an input-output relationship. I mean, bijection. So let's go ahead and write it. Here are the elements I get to plug in. And the outputs are also those kinds of things. So here's one. I'll just go ahead and put 2, then 1, and then not 2 again. No, not a bijection. 3. There you go. There's only one. That's all you have left after I chose 2 and 1. Okay, fantastic. Or as the book likes to put it, book. Here you go. Inputs. An output table. Okay, 1, 2, 3, and 2, 1, 3. Okay, pay attention, class. After you're watching this on YouTube, when I put it on YouTube, So pay attention. We are now going to execute P times Q. Execute P times Q according to our convention that we are establishing right now and in line with the book. P times Q means the composite function P circle Q, which is first do Q, then do P. First do Q, then do P. We will stay with this convention of composition for the whole class, okay? So let's do this. Otherwise, your groups will be all what's called the opposite of a given group. If you have a group, there's actually a group called the opposite group, which is that you turn the multiplication around. Anyway, so let's do this. Let's, but you know, it's an isomorphic group. Anyway, first do Q, then do P. Okay, so we're gonna find this element. So what is this element? So what is PQ in input-output notation? Okay, so what is PQ? Well, tell me what it did to 1. PQ of 1 is P of Q of 1. That's how you do it. Okay, so this is P of Q of 1. Q of 1 is 2. It's this green 2. And then it's P of 2. Now, P of 2 is this red 1. Okay, so where did 1 go? 1 was sent to 1. Awesome. Okay, so what is P of Q of 2? It equals P of Q of 2, which is Q of 2. That's 1. P of 1. That's 3. Okay. P of Q, compose 2 bijections. We're just composing, folks. This is the most elementary thing that you can do when you have 2 functions whose domain and range and codomain are in alignment properly. Okay, so P of Q of 3. Okay, Q of 3 is 3 again. Very confusing. All right, and now P of 3 is 2. Okay, so now you take the input-output relationship. Okay, so now you have to draw this in, out. In is 1, 2, and 3. 1, 2, 3. Outputs 1, 3, 2. Or as the book likes to write it, put it on its side, okay? 1, 2, 3, and 1, 3, 2. This is P times Q in the symmetric group S3, okay? So that's how you multiply in S3 and in S4 and in S10 billion. All right, so now, class, go into Sn. I've given you some homework where you're forced to multiply things and compute the inverse of a given element. Try to do that too. Figure out what's the inverse of P in this example. Like, what's P inverse in S3? What's the inverse map? Inverse permutation. The inverse of the bijection. Go ahead and practice as much as you can in S3, S4, etc. And we'll say some more concrete things about Sn next class. And I guess I will have office hours on Friday, so we'll also be able to talk about you want to do a bunch of calculations in symmetric group on Friday. we can talk about that. We can clarify confusion, but on Friday we'll have to I'll have to introduce another way of encoding a permutation, which is sometimes useful. It's called the cycle notation for a permutation. It's not hard. It's just another way of encoding a permutation. Rather than this input-output table, it looks slightly different. Okay, so that's what we have in store for us on Friday and for office hours on Friday, which I'll tell you, we'll discuss the time on Discord and fix a good time. Okay, now I'll look briefly at this degenerate chat. Oh, okay, I have to thank a bunch of people. Amira, thank you. Rintaru, thank you. Cortical, thank you for following. Mox19, thank you for being here. Let's go look. Is this open class? I guess so. I mean, it's not open really because you can't access the Discord. So no, it's only the lecture is available. Shanghai Tropical Geek needs their daily Shanghai 1, 3. Here you go. Let this Shanghai protect you from 5G radiation for the rest of this day. I hope you put your face close to the screen because of the inverse square law. Okay, it's my birthday today. Wow, happy birthday! Okay. Anyone want to redeem some recorder so that I can play happy birthday? Anyone? Is there anyone out there who wants to redeem recorder? Ah, there you go. Okay, everybody. Okay. Tropical Geek themselves redeemed recorder. That's sad. Okay, but awesome. But so did some other people. Let's see. I just have to remember if... Okay, I need to do some scales, folks. I just have to get warmed up. Okay. Ready? Here we go. Perfect. That's for a Tropical Geek. The bitrate went... There was a little bit of lag in the middle there. So what lag does is it sometimes shifts some the sort of audio file frequencies down a notch. So if you heard a little bit of that, that's because of the lag in the internet right now. But on my end, it was pitch perfect. You're gonna have to believe me on that. Okay. Fly to the Bumblebee. You know what, Roosta? You always request Fly to the Bumblebee. So there it is. Now, no longer can you request that. Okay. Let's see here. It's not meant for the recorder. It's more of like a violin or flute. Sounds more like a fly. Yeah, yes. The flight of the fly. Yes, that's what it sounds more like a fly. Yes, absolutely. Okay, folks. So you know how this goes. I have to go and make up some random garbage for my Calc 2 class. Now, none of them come to this class, so they don't know that I just like I'm on autopilot, and I make up the examples like 5 seconds before. So yeah, I gotta go do that and make sure I know how to do trigonometry or something like that. So I also have to eat, and so time to wrap things up here. Time to wrap things up. Now let's see, who is out there? Thank you to everyone who showed up. You didn't have to, and I'm not sure why you're here. We learned about cosets today, left cosets. You could have done the same exact arguments for right cosets, but it's very important for you to understand that a left coset need not be a right coset. That's something you should try to tease out in specific examples in your favorite groups. Take your favorite group, your favorite subgroup, and ask, do the left cosets and the right cosets kind of align together? Are they the same concepts? Do they form the same partitioning of the group G? No. But that's warning. Oh, Dr. Young's lab was here? Did we not shout Dr. No, Dr. Young's lab wasn't here. Oh, I see. Yeah. What's for lunch? I have no idea. I'm just gonna like graze on the grass outside. Get that nitrogen in me. Matrix algebra? Well, indeed. Matrix algebra, when it comes to invertible square matrices, that is just group theory, sort of. It's group theory in GLN, the matrix group, the general linear group, n by n matrices. What exactly is abstract algebra for? Abstract algebra is for everything. It's almost like, where does abstract algebra not arise? That's your question, Rinterroot. It's one of those situations where after thousands of years of doing math, people noticed that many of the structures in mathematics share some common properties. Then one person went, maybe not one, maybe it was several. They went and said, you know what? Let's stop reinventing the wheel every time we encounter these kinds of objects. Let's go and just write out all the things that are true in super generality so that we don't have to waste our time rediscovering various facts. And there abstract algebra is born. And you can't do math without saying the word group anymore. Like, it's open any paper by anybody, you will find the word group somewhere. Like, it's a 90% chance, I would say. Okay. Basis of statistics. Actually, some algebra does appear in statistics, though I'm no expert. I do remember it appearing when I had to take classes. It's not really the statistics that I remember it appearing in, but it was in the measure theory. Sort of measure theory? Yeah, there's something called a sigma algebra. Anyway. Okay. Anyway, so here we go. Where are we going? Let's see. Let's just see. Raid. Okay, where's my boring music? It's out there. Who is out there? Oh, I use Notability. I get this question a lot, actually. I don't know. Is it like somehow really fancy looking? That's what people seem to think. I use something called Notability on iPad. So, I don't know. Does it look particularly like fancy? Because people keep thinking it's some, keep asking. But yeah, maybe it's just the smoothness of the iPad, and I don't know. I'm no computer person, so. It's the colors. Oh, look at that. Look at that. We have a command now. Notes. iPad OK. You need to frequently ask questions. Maybe once I learn how to type that down there. The handwriting. Well, today's handwriting was kind of bad, I have to say. I was getting rushed because of my 45-minute class, which of course I didn't make. I didn't actually get in 45 minutes, but it was close enough. Yeah, so I started, look, oh, the handwriting's really good. Good. And then it just started going crazy. Wait, it's still good. Wow, I have really good handwriting. Okay, never mind. I'm just have good handwriting. Okay, let's see. Who should we raid? Okay. Who's on? I don't know. Maybe we shouldn't raid anybody? Do you guys want to make money again? Do you want to make money? Or no? Are you guys tired of making money? How do I do this? Who is Andre H? Oh, Maka? Okay. I know Maka Waka. Meaning I know of them. So here you go. Let's go take a walk with Maka Waka. Alright, we're gonna go raid Maka Waka and go accompany them on their walk. They do a lot of walking, and it's very therapeutic and nice. Just sort of hang out while they're walking around. So it looks like they're walking by some trash cans right now. So go ahead and go say hi to Maka as they walk by some trash cans. All right, here we go. Am I still